All right. Um, by the way, it says it's section 3.2. In the old book, it was section 3.2. This is section 5.2. Just didn't want anyone to be confused. I kept the notes from the old book because they were perfectly good. So consider each of the continuous differentiable functions on AB shown below. At how many points will the slope of a tangent line be parallel to the slope of the secant line that's shown? So for this one, at how many points on that graph will I have a tangent line that's parallel to this line? Yeah, there's going to be two. And for some people, they have trouble seeing this. I think one of the easiest ways to see it is rotate your paper slightly so that the dotted line is horizontal. Then I think it's easy to see there will be one right about it there and another one right about there. Right? In this case, there were two. In this case, how many will there be? Just one. Somewhere right in there. So if I connect those 2 points with a continuous differentiable curve, so that means no pointy bits, right? And it has to be continuous. You can't stop and start. Is there any way that I would never have any? Yeah, you're always going to have at least one. Could you have dozens of them? You could. It's possible. But you're always going to have at least one. So the mean value theorem is something that's called an existence theorem. It tells you that under these conditions, you're going to have a tangent line that's parallel to the secant line. It doesn't help you find it at all. It just tells you there's going to be one. Okay? Now, the slope of these blue lines, well, that's the derivative at one of those points, right? The slope of the secant line is the average rate of change. Right? The average rate of change is the change in y over the change in x. So that's just the average rate of change. So basically they're saying if you have what is sometimes called a well-behaved curve, which is one that is continuous and differentiable, then at some place the average rate of change has to be equal to the instantaneous rate of change. If you drive somewhere and it takes you 2 hours to go 100 miles, what is your average rate of change? 50 miles an hour. At some point, did you have to be going 50 miles an hour? Yeah. Now, is it possible you were doing 50 the entire time? Yeah. Is it possible that your speed was 50 at, 18 different times, but most of the time it was somewhere else? Yeah. Okay. But that's what the mean value theorem says. So the actual wording of the mean value theorem is one of the few long theorems that I have totally memorized. You should probably commit this one to memory. I usually don't ask that for really long ones like this, but this is important enough. So if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a number c in the open interval from a to b such that f prime of c is equal to f of b minus f of a over b minus a. It's lots of moving parts, but you have to be continuous on a closed interval. That means you need to include the endpoints. You can't have a hole at one of the endpoints. Because if you have a hole at one of the endpoints, you're not going to be able to do the average rate of change at all. So it's got to be continuous in between and at the endpoints. It doesn't have to be differentiable at the end point. It can bounce and do all kinds of crazy things at the end point. We don't care about that. It just needs to be smooth in between the two. If those two things are true, then there's got to be a place in between the two where the derivative, which is the instantaneous rate of change, is equal to the average rate of change. So another way of saying this is, or the instantaneous rate of change equals the average rate of change. At some point. At some point, your instantaneous rate of change has got to be equal to your average rate of change. Now, notice there are things where this doesn't work. For example, your grades. If you have a 93 average, did you ever have to make a 93? No. Okay? Doesn't work that way. Why? Because grades are not continuous. Okay? So those two first things are vitally important that you check first before you start going on to taking the derivative and finding the average rate of change. For example, determine whether the mean value theorem applies to the given function on the given interval. If so, find the point at which the instantaneous rate of change is equal to the average rate of change. That is, find the value that is guaranteed by the mean value theorem. And that's usually how they write them on AP exams. Find the value of C guaranteed by the mean value theorem if it applies. All right, so first, let's look at this. Is this function continuous? Is there any place that I can't take an absolute value? Okay, so f of x is continuous. On the closed interval from -2 to 2. Is this function differentiable on the open interval from -2 to 2? Why not? Where? No. Not for this one. This is not the absolute value of x. This is the absolute value of x plus 1. So at x is -1. Yeah, f prime is not differentiable at x equals -1. The mean value theorem does not apply. If you were graphing this, graph looks something like that, right? It's got that corner down here where the derivative from the left at -1 is not equal to the derivative from the right. All right, let's take a look at this one. So I've got f of x is equal to 5 minus 4 over x. Where is this function not defined? Because it's not defined everywhere. Where is it not defined? Where are fractions undefined, guys? This goes back to when x is equal to 0. because that would make the denominator 0. Is that in my interval? No. Okay, I don't have to worry about it then. F of x is continuous. On the closed interval from 1 to 4. Unlike the last problem where taking the derivative would have been a pain, you could do it with a piecewise function. Here I can take the derivative. F prime of x equals, well, let's see. Think of this as 5 minus 4x to the negative 1. So that would be 4x to the negative 2. Where is that not defined? Wow, you guys are killing me today. And x is 0, right? Fractions are not defined when the denominator is 0. That's it. They're defined everywhere else. Still not in my interval. So f of x is differentiable on the open interval from 1 to 4. So the mean value theorem applies. So we need to do two things. We need to find the derivative. Oh, we've already done that. Nice. And we need to find the average rate of change. So the average rate of change of f on this interval is going to be equal to, well, let's see, f of 4, that'll be 5 minus 4 over 4, minus f of 1, which is 5 minus 4 over 1, all over 4 minus 1. So that's 5 minus 1 is 4, minus 5 minus 4 is 1, over 4 minus 1, hey, how nice is that? It's 1. And I want to find the value of C guaranteed by the mean value theorem. So that means this derivative needs to be equal to 1 at some point. So 4 over x squared is equal to 1. Means that 4 is equal to x squared, which means that x is equal to, I heard three things, what? Plus or minus 2, exactly right. But notice, only one of those is actually in my interval. So the value guaranteed by the mean value theorem is that C is equal to 2. We have to throw out the negative 2 because it's not within our interval. All right. Let's try this one. F of x is equal to x minus 3 to the 4/5 power. Okay. In order to talk about the domain for this, you need to understand when it's to the 4/5 power, what is another way to write that? As a root? Yeah. It's the 5th root of x minus 3 to the 4th power. We talked about fractions where they're undefined. Where are roots undefined? No. Some of them are, but not all of them. Can you take the cube root of a negative number? Yes. Can you take the square root of a negative number and get a real answer? No. So what about the fourth root? Can you take the fourth root of a negative and get a real number? No. Can you take the fifth root of a negative number? Yeah. So this is defined for all values of x. So f of x is continuous. On the closed interval from 0 to 5. Well, now let's take the derivative. F prime of x would be 4/5 times x minus 3 to the negative 1/5. Let's write that in root notation. Maybe that'll make it easier to see that there's a problem here. So this would be the fifth root of x minus 3. Sorry, that is a 5 in the root index. I kind of squeezed it in there. Where's the problem with this fractional expression? Can't be 0 on the bottom. So that means x can't be 3. Oh, that's within my interval that they gave me, isn't it? So since this does not exist at x equals 3, f is not differentiable. On the open interval from 0 to 5. So the mean value theorem does not apply. So before you use the mean value theorem, you got to make sure that the mean value theorem applies. Now, we won't get into it too much at the moment, but just something to think about is that just because those two qualifications don't happen doesn't mean that you can't have a place where the instantaneous rate of change is equal to the average rate of change. It's just not guaranteed to happen. Spinning beach ball of annoyance. All right. So let's look at this last page. So I don't remember if I got this from an old AP question. It looks like one. So a particle moves along the x-axis with velocity v of t, where v is a differentiable function of time t. Let's stop there. If v is differentiable, what else does that tell you about it? It's continuous. Differentiability always implies continuity. Okay, so we have a well-behaved curve. The velocity at selected values of t is given below. I'm going to at least get the A and B part done here. What is the fewest number of the times that the velocity must be 20 centimeters per second on the interval from 0 to 12? What's the fewest number of times that it must be 20? How come? Okay, that doesn't really explain, but I know what you're saying. Say more. Okay, so since v is differentiable, it is also continuous. Ben, do you know the name of the theorem that you were using? Very nice. So, IVT applies. Since V of 0, which is equal to 37, is greater than 20, which in turn is greater than V of 2, which is 17, and V of 10, which is equal to 17, is less than 20, which in turn is less than V of 12, which is 38. V must equal at least twice. Okay, notice how we're justifying it. Okay, you have to talk about the 20 being between those two values. All right, next, explain why the acceleration of the particle must be 0 at least once on the interval from 2 to 10. So on the interval from 2 to 10, why does the acceleration have to be 0 at least once? How do you know it changes direction?
Well, I don't know that it changes direction, but it goes.
It. Let's not use it.
The velocity starts off negatively,
The velocity is 17.
I don't really know how to explain it. It goes down, it goes back up.
The velocity decreases then increases? Well, I agree that the velocity decreases then increases, but that doesn't guarantee that the acceleration is ever going to have to be 0. Notice, both of these are 17, right? What is the average rate of change of the velocity on the closed interval from 2 to 10? Exactly right. The average rate of change is 0. And we're talking about acceleration, which is acceleration is the derivative of the velocity function, right? So, since acceleration is equal to v prime of t, and we know that the average rate of change is 0, so that's the instantaneous rate of change. Oh, this is the mean value theorem. So since v is continuous, on the closed interval from 2 to 10, and differentiable on the open interval from 2 to 10, the The mean value theorem guarantees a value of C on the open interval from 2 to 10 such that V prime of C, which is A of C, is going to be equal to 0. At some point, the instantaneous rate of change of velocity has to be equal to the average rate of change of the velocity. Yeah.
Could you think of it as like acceleration was negative at the beginning and then it became positive, so acceleration has to be
Yeah, the
positive.
problem is that if you do that, and you can, you have to say that since the average rate of change of the velocity from 2 to 4 is negative, at some point the acceleration had to be negative on that interval. And then you can't just say it is negative here because we don't know at 2
Okay.
that it is. You see what I'm saying? Because this could have sped up, slowed down, sped up, slowed down all over the place in between the two. Okay? All right, those were the two long parts of this. Estimate the acceleration at 9. Okay. Well, if I want the acceleration at 9 and I want to estimate it, well, the acceleration is the derivative of the velocity, right? I don't have a function to work with, so all I can do is find a slope that is the smallest. I'm going to use this interval. Why that interval? Because this is only 1 second interval. If I go down to 6, it's much further away. If I had that this was 8, I would probably go from 8 to 10, so that I'm taking the average of those. But A of 9 is approximately 17 minus 6 over 10 minus 9 is 11 over 1, which is 11 centimeters per second per second. Right, we did that earlier in the year. All right, what's the last question on this? Is this the one? Yeah, what's the maximum velocity of the particle on the interval from 0 to 12? Yeah, you fell for it. I put it on there so that I hope that someone falls for it every year. And they do. At least one person every year falls for it. We don't know. We have no way of knowing. Because have they given us the velocity for every value of t? No. I mean, it's possible that at some point the velocity was 4,000 centimeters per second. We just don't know. So for part D, it cannot be determined from the given information. All right. Was that it? Was D the last part? Yep. Okay.